I'd like to talk a little bit about the physics experiments that I have created to help scientists come to the conclusion that this indeed is a virtual reality. Before scientists will believe anything, this is the way science works, they need an experiment that confirms that belief. That's what makes a belief turn into a fact. You might believe that something will work a certain way, but until the experiment is done, it's not a fact. It's just a theory or even just a hypothesis. So I have created a set of experiments that could be done which lend a lot of evidence to the idea that we're living within a virtual reality. I wouldn't say they prove we live in a virtual reality because science really isn't about proof. Nothing is really proved anymore in science. In the day of Newton, we thought we could prove things, and then we had laws like Newton's laws, but we don't have laws anymore because we realize we don't have all the information. More information will come in the years ahead and in the decades and in the millennia ahead, and to say that you have proven something is a bit of a stretch. So these experiments will lend a lot of credibility to the idea of virtual reality. I have a whole set here, and some of them are there just to lead up to the ones that are more important. Some of them are there to test new ideas, new things that have never actually been studied before, like the observer. Does the observer merely have to look and see the data, or does it have to be recorded? That's not really been tested as far as I know, as far as I've been able to find out in the literature. Does that observer have to be a human being? Or could it be anything that's conscious, that observes the which-way data? In other words, which slit that the particle goes through, which hole the particle goes through. These are questions that haven't really been studied. There are several others in that line that I've done maybe 5 or 6 variations of that. And this is just for my own information, well, for the information of science, because these are areas, again, unstudied. I have one experiment, and I call that experiment 2. I think it was the second one in my talking about the experiments, which you can find, by the way, on my YouTube site as MBT-LA. I gave these in LA in October 2016. And experiment 2 probes the idea of the observer and what the observer observes. Does the observer need to observe recorded information? If a particle is detected, is that enough to create the which-way data? Or does that detection actually have to be recorded? That's a key idea. Now, virtual reality can work just very well and simply if the observer sees, records, shall we say, that's kind of what sees mean, records the which-way data, and that which-way data is available for any observer to look at. Now, that's typically the experiment that's done. But the question is, if we just did the detection without recording the data, what would happen? So I think that what would happen is that we would not get which-way data because we wouldn't have any information that a consciousness could look at. So it hasn't actually come into the reality yet. Of course, that could be wrong. Like any experiment, you don't really know what the answer is until you do the experiment. It's possible that the larger conscious system could just decide that this idea of entanglement is enough to create information, and because of that, it doesn't need the recorded data. Now, that's what most physicists believe is true. I'm going in the opposite direction, saying, could be true, but I'm not sure. And since there's no research that actually answers that question, then I did experiment 2, so I could answer that question. Now, the other experiments that I have, the ones that are most important, really don't depend on the answered experiment 2 at all. They're completely independent of that. So it doesn't matter which way that number 2 turns out. These other experiments are quite independent and will stand on their own. And they do some rather miraculous things. There's one that allows the experimenter to determine how an atom will decay, what direction the decayed particle will go in. In other words, what direction the radiation, the resultant radiation from the decay of the atom, which direction will that go in? Now, that should be impossible. That should be completely random. But I think that in this experiment, I can kind of trap the system, the larger conscious system, or you might say reality, between a rock and a hard place and force it to show us some of how it works. And that I indeed can, ahead of time, predict how an atom will decay. Also, I have an experiment where there's a beam splitter. A beam splitter is a thing that's used in optics, where a photon will get to a beam splitter and it does one of 2 things. It either transmits that photon, in other words, the photon goes right through it, the light goes right through it, comes out the other side, or it reflects it. It's called a half-silvered mirror. A half-silvered mirror, you can think of it, this is not exactly the way they're made, but you could think of it as a piece of glass that has a lot of little dots of mirror on it, a lot of silver dots on it. But the silver dots just cover half the area, and the other half of the area is just clear glass. So depending on where the photon hits, if it hits one of those little mirror spots, it gets reflected. If it hits the non-mirrored spots, it goes straight through. Now that's just a metaphorical description. Not really made that way, but that's the function. So light hits it and is either reflected or transmitted. And in my experiment, I can predict which one that's going to be, whether it actually is reflected or transmitted ahead of time before it happens. Again, that is impossible. But I think that's doable in this experiment. And you see, the only way that I could predict that would be if this indeed is a virtual reality and the results are indeed pulled from a random draw from a probability distribution of the possibilities. If that's the case, and that's the way reality works, then that would explain these miracles, if you will. These things that are impossible would be explained. Other than that, they'd be extremely hard to explain, because I can't think of any other way other than virtual reality that can explain these things. So that's why, if they work the way I hope they will, we will have some very strong evidence for virtual reality being a real thing, the way this universe works. So those are a few comments about the experiments. Now, in all these experiments, the larger conscious system has choices in those experiments. This is a thinking, aware, knowledgeable system. It's conscious, you see. So this is a consciousness system. The system can make decisions and choices. There are multiple ways that it could have these experiments come out. It could decide to do it this way, or it could decide to do it that way. And I've taken some of the things I've known in my own research about the conscious system and some ideas, such as the system is finite and therefore has limited capacity. Therefore, it will always take the path of the most efficient computation. Unless, of course, it has a good reason that it doesn't want to do that. You see, it could do things that aren't efficient on purpose for some other reason. So my criteria for believing that these experiments might produce some very outstanding evidence depend on my assumptions that the computation will be parsimonious. That means it'll be very efficient. That the system primarily wants to maintain consistency in this reality frame, in this virtual reality, because an inconsistent reality is just not a very good schoolhouse, not a very good learning lab. And because the system is virtual, it only produces data streams to players, and the reality actually exists only in the mind of the player. So if things are done that never reach a data stream, therefore never get to the mind of a player, like a detector that's just detecting, but no information is ever created that a player gets, then my thought is that the system really doesn't care about that, because the reality is generated in the minds of the players. That's the nature of a virtual reality. So with these concepts, I've come up with some experiments. The experiments are based on my understanding of how virtual reality works, and they, of course, like any experiment, may work the way I think or may not. But I'd really like to know the results. That's how science works. If I will be a winner whether they work the way I want them to work, or I shouldn't say want, if they work the way I think they'll work or not, because I will learn something. That's how models grow. You get information back from experiments, and if it surprises you, then you have to adjust your model, change the way you look at the world. If it confirms you, then you know that the assumptions you've made have been good assumptions. So I think it's exciting. I'm looking forward to it. And I feel like I will be a winner in either case, because I will learn the things that I need to learn to improve the theory that I have. This theory has solved so many outstanding problems that it's hard to believe that it is entirely wrong. Now, the way I interpret this virtual reality into the world of quantum mechanics and physics, that's kind of stands on its own. That's its own little adventure of mine, taking the virtual reality and trying to explain quantum mechanics problems with it. If that fails, well, all the rest of the my big toe reality frame and model still stands and still solves all the problems that it solves, but perhaps I'd have to rethink how it is I'm applying it to quantum mechanics, and that would be very good, very informative for me. And if they do come out the way I say, then they will launch, I think, a revolution in science. They will speed up what's going to happen anyway, but they will just build a fire under it to find these things that are totally impossible, would take a miracle to do, that you can do. So that's my experiments, and I'm excited about it. I hope to get them done in the next year or so. And when I do, I'll have it out on YouTube, just like everything else. The experiments were first presented October 29 and 30, 2016 at LA, California. The name of the presentation was Reality 102. The first day I talked about how does it work, and that was a talk about virtual reality and then presenting the experiments. The second day I talked to all those who really weren't so interested in physics and answered the question, why should I care? In other words, why is this important to the man in the street and not just to the physicist? You can find this talk on YouTube. Just do a search for Reality 102 or do a search for MBT-LA 2016. Either one of those should take you to this video. So I'm just going to go through it and explain the experiments to you. I'm going to skip all the rest of it except talking about the experiments. So if you'd like to see the rest of it, you'll have to find that on YouTube. In the first part, I talked about virtual reality. I talked about action at a distance, and then I presented the slides. And as you see, these slides take up 35 slides of the whole day. So we're going to look at those 35. We will not look at all of them because some of them will just be notes and more information and details, and I won't get into that much detail today. I just want to point out each experiment and what's significant about it and what we're supposed to learn from it and what result is predicted for it. This is the starting point. This is an overview of probably 10 hours of video and lecture that would bring us up to this point where we would talk about the experiments. But it's all summarized in a couple of sentences here, and this is really all the background you need to know. I'll give you a moment to look at this. All right, here we are with experiment 1. This is slide number 33 in the presentation. Okay. The point of this setup is to show that the detectors detecting at each slit and any theoretical or potential measurable availability of the which-way data is not important. The only data that's important is certain availability of objective measured which-way data. Okay. So you see we have the particle generator shooting particles at 2 slits, and those slits each have their own detector, D1, D2, in the circles right at the bottom of the slits. Those 2 detectors send a pulse on, and that pulse gets to D0, that little blue ball there. At that blue ball, there's a repeater that just accepts the pulse and produces a pulse of its own. And I do that so that there can be no difference between the pulses coming from D1 and D2. They should be identical. They're exactly the same sort of detector, but who knows? Sometimes individual electronics will have their own signatures. So this makes sure that there is nothing about those 2 pulses that come from one from D1 and one from D2 that is different. So then the pulse goes into R1, which is a recorder. So as you can see, this is an eraser experiment. As a particle goes through a slit, that creates a pulse in a detector. The detector then goes into a single point at D1 before it goes into R1. So by the time it gets to R1, there's no more information about which slit it went through, just only that a pulse arrived. All right, you see behind the double slits is the detectors, and behind that is the patterns that we'll look at. Sometimes we'll get a diffraction pattern, sometimes we'll get the 2-bar or the particle pattern. All right, we have 6 experiments in this A. So we will look at the first one now. Experiment 1A represents a standard eraser experiment. Okay, very much like I described in just looking at all the experiment 1s. Because we have identical pulses generated by a particle going through either one of the slits, and once those particles come together and have just one entry point into R1, then there is no more which-way data because all the pulses look the same. All right, now this should produce a diffraction pattern because there is no which-way data. This is a conflict with traditional physics. Traditional physics sees an entanglement between the particle, the slit, and between the slit and the detector, and therefore information gets passed on to R1. I say that's not true, that if you don't have objective recorded information, that's the same as there having never been any information in the first place. So that's what's interesting about this experiment. So we'll go on to the next one. This is 1B. Now, you see that we've taken R1 and we've moved it further away. And we've moved it so far away that the particle will go through a slit and hit the result screen before a signal gets to R1, telling R1 which slit it went through, or not. So the distance between the slits and the recorder R1 is greater than the distance between the slits and the result screen. So now we're going to have a delayed eraser experiment where we will actually erase the data after the data on the result screen has already been recorded. Okay, this is called a delayed eraser. Other than that, it works the same way as we talked about it before. You have a pulse will go through one slit or the other. The detector, D1 and D2, will produce a pulse. That pulse will travel down the wire until it gets to D0, and there it will descend into R1 and be recorded. Okay, so these pulses are anonymous. So after it gets to that D0, any information about which path it came through is erased. We know the which path information before it gets to Z0 because these two wires that carry the path of D1 and D2 are separate. But that's only potential which way data. It's there in the wire. If you want to look, you can see which one of those wires has the pulse in it. But after it gets to D0, that's gone. So this is a delayed eraser experiment. And again, I would say we get a diffraction pattern for basically the same reasons. Even though the eraser is now after the result screen, that will make no difference. Okay. The result screen data, R3, is not looked at until this experiment is over. Okay, we'll go on to the next experiment. Okay, this is 1C1, and now we have made a little change in the last one. We have added what I'm calling a which way data device that randomly injects which way path uniqueness into any pulse traveling that path just before the two paths converge. So I will be able to make this which way device, I will be able to push a button or have a random number tell this little device to turn on or turn off. If it turns off, then again, the paths are not unique, so the pulses look exactly the same. They're anonymous. But I can, at any moment, randomly or on purpose, change that and interject a 1 in the data D1 and a 2 in any pulse data that comes in D2. So now the two paths are uniquely identified, and even though they both go through the same wire at D0, they carry this uniqueness with them. So they've got a tag now attached to the pulse. Okay. So what we're going to do, you might have figured this out, is we're going to send a particle through the slit. That particle will first get to the screen and be part of a either diffraction pattern or a particle pattern, that is a wave pattern or a particle pattern. And then, after we have that dot on the screen, we are then going to say if it was off and all the data was anonymous, we will switch on this WW device and put uniqueness into the detection process, and suddenly we will have which way data created after the particle has already hit the screen. Okay, so when the particle hit the screen, there was none, but later there is some which way data. So if you like, this is the opposite of an eraser experiment. This is not a delayed eraser, this is a delayed inserter. So we're inserting the which way data after the screen data already has done its thing. So what my prediction is here is that when the which way device is off, we'll get the diffraction pattern because there'll be no which way data. And when it's on, we will get the particle pattern, the 2-bar pattern. Okay, which means because there will be which way data when it's on. So it will know, even though it seems like it has to know in advance because that switch isn't going to be thrown until after the answer is already on the result screen. But I think that will make no difference. It'll work the same way. All right, let's go on to the next. And I'm not going to explain all the things on this slide. That's a little much for detail in this particular talk. But if you want to know more detail of exactly what's going on and how it's working this way, go to this video on YouTube, and you'll find there's a lot more information here than what I'm telling you at this time. All right. And here's a little bit of that information. I'll just move through that. Here we get on to 1C2. Now, this is the same experiment that we just did with a very interesting change to it. And that is that before we actually start our experiment, we are going to have particles thrown at these slits and see where they land on the detection screen. And we're going to do it with that random which-way data injection. We're going to do it with that turned on, say 100,000 times, and then we'll turn it off and we'll run particles through it another 100,000 times. So we'll have a result screen with 200,000 points on it, and we will know whether those points are associated with a diffraction pattern, that is no which-way data, or a particle pattern, that is we do have which-way data. So we will know that. Now, we will do our experiment. We have this data collected, and we will do a probability calculation for any point that hits the screen now when we actually do our experiment. I will know if a point hits the screen at a particular place, I will be able to tell what the probability is of it being in a diffraction pattern or in a particle pattern. See, what I'll do is I'll take all that data, that 200 points, and I'll look at every point on the screen, and I'll look at the 5 closest data points that we measured out of the 200,000 points. I'll look at the 5 closest data points to that point on the screen. And let's say 3 of those closest points were diffraction patterns and 2 were particle patterns. In that case, the probability of that point being a diffraction pattern will be 3/5, 3 out of 5. The probability of it being a particle pattern will be 2 out of 5. So see, we'll have a probability of being in a diffraction or particle pattern for every point on the result screen. Now we're going to hook a little microprocessor. You see that attached to R3. That's the recording device for the result screen. That microprocessor is going to apply that little probability algorithm that we're going to make, is going to apply that. Actually, it'll be a lookup table. It'll look up the position on the screen, and then it'll output a probability distribution. We're going to know that probability distribution before the particle gets to the which-way data injectors. So when the detection signal is about where those dashed blue lines are, the detection signal coming out of D1 and D2, by that time we will already have a prediction of whether that particle is in a particle pattern or a wave pattern. Okay, the wave pattern being the diffraction pattern, the particle pattern being the 2-bar pattern. So now, knowing that, we can randomly change that device that produces either random which-way data. When it's on, we get which-way data and get a particle pattern. When it's off, we get no which-way data, which then will give us a diffraction pattern. But we'll already have the prediction of that from the result screen before that random number is chosen to decide whether it's on or off. So that is really backing reality into a corner and forcing it to show us some of its secrets. This random number generator can be a natural event-based random number generator. That is something that produces a random number based on radioactive decay. Now, radioactive decay is entirely random. The direction of that decay is random, and we're going to be able to predict how that radioactive nucleus is going to decay, whether it's going to send a particle to the detector on the right side or on the left side of it, and we will predict that before the atom decays. Okay, before the element shoots that particle off. Now, this should be impossible according to standard physics. You shouldn't be able to predict how a particle will leave a nucleus in a radioactive decay. But we're going to do that. So we'll predict it because of this microprocessor that we have. Will be telling us what part of the pattern it's in. And if it tells us it's in a diffraction pattern, then we'll predict that the random which-way data injection is off. And if it tells us it's going to be in a particle pattern, we'll predict that the random which-way injection device will be on. And if you want to know why we come to that conclusion, you'll have to look at this and read all the details. We don't really have time for that, but just want to tell you what the experiment's doing. So this is a pretty novel experiment. It does something that I don't think any experiment's done before. In order to do this experiment, we're going to have to deconflict our wave and particle data on the screen. And how we do that is by adjusting the distance between the slits, the wavelength, if it's a light that we're using, or the kind of particle, like an electron that we're using. And we adjust the particle or the wavelength, the separation, the distance to the screen. All of those things will make a difference as to exactly where the particle hits on the screen. And we will adjust those so as to deconflict those two patterns, so that we know that if we get a dot someplace, we can have a better probability that we know what pattern it comes from. So this is just a picture showing you how we will do that. And it won't look as good as this picture. Obviously, we can't make all the dots that are in a particle pattern, the two bars that you see, the two blue bars. They're not all going to line up very neatly and not touch any of the other patterns. They're all going to smear a little bit over each other, but that's all right. That won't hurt the experiment. If there's a probability of 70% that it's a diffraction pattern, then 70% of the time we should get a correct guess. So it will work, even if only a small number of particles have a 100% certainty of what pattern it comes from. Now we have the 1D, E, and F, which are very similar to what we've just done, except we no longer are going to talk about the which way device that we talked about before. So these are a little different. This is just a standard double slit experiment. There's no eraser here because these detectors now are outputting a unique pulse. So the pulse that they put out can be identified in R1 as being from slit 1 or slit 2, detector 1 or detector 2. So that detector maybe has a little header material goes with the pulse that says slit 1, and the D2 has a little header that goes with the pulse that it creates that says slit 2. So now there's no eraser at D0. So we collect all the which way data, and what you see, what we're going to get is a particle pattern, the 2-bar pattern. That's just standard double slit. Okay. Now we're going to make a double slit with an extended distance and time for the signal to get out to R1. Okay. So again, the output's unique. The time it takes for a particle to get out to R1 is longer, quite longer than the time it takes the particle to get to the screen. And we're also going to find a particle pattern. It makes no difference whether this R1 gets its data before or after R3. R3 is the collector for the result screen. Okay, it really doesn't make any difference whether it's before or after. We're still going to get that 2-particle pattern. Okay, next. All right, now 1F. This time we're going to introduce a fast switch. Rather than put uniqueness in each one of the pathways from detector 1 to detector 2 to R1, we're going to actually put a switch right after the two signals go together. What that switch does is it disconnects R1. So it takes R1 offline, breaks that circuit. So R1 won't get anything. Before, R1 was getting pulses, but pulses that were anonymous. Here, this fast switch will create a delayed eraser. When the switch is on and R1 is disconnected, that data is going to be erased in the sense that it won't be recorded. It's not that it's recorded and erased, it's just never recorded. So we'll call that eraser. So this is a little different than what we've done before. Puts it all in a little different context, and fast switches are simple things and inexpensive things compared to which way data injectors. So this will be a little more efficient. And here you see we're going to play the same game as we did before with a microprocessor. And this time what we're going to be able to do is we're going to be able to predict, again, another random number. We're going to let a random number predict, or a random number determine whether this switch is on or off. And we will again be able to predict that random number before the atom ever decays to give us that random number. All right, very similar to the one we saw before, just done differently, which has a little different physics to it, but comes out to the same result. Now here's experiment 2. And we've already done this in experiment 1, but I wanted to bring this out on its own, separate, with no confusion of anything else going on, just to test this idea that if you don't collect the data, then you're going to get a diffraction pattern. And it doesn't matter how you don't collect the data. You can don't collect the data because you don't have detectors, or you can not collect the data because the output of the detector is not being recorded. So here we see both detectors are turned on, both recorders are turned off. R1 and R2 are turned off. It's just that simple. So there's not a lot else going on, and I wanted to do this just for the simplicity of it, to put this issue, which is a contentious issue now. Again, traditional physics does not agree with me here, so we'll see. Coming up next, we're going to talk about conscious observer connection. Okay, so what I have done here is a kind of a study in how one defines whether the which way data is recorded. Can it just be recorded in the mind of a man? In other words, a man sees which slit it goes through. Does it have to be recorded on some kind of electrical recorder, or written down on paper, some kind of hard copy? What are the requirements for this data being recorded? It's not clear whether it's just a person sees it, or whether or not it has to be something that is objectively available to everyone. Now, it could be subjectively available. The man who sees it could say, "Oh, I see it," but though he makes that announcement, that doesn't make it objective. It's subjective. Okay, so here's going to be a whole series. You see, it goes 3A1 all the way out to 3C. And all of these are variations on different schemes for defining what makes which way data and what makes which way data go away. Okay, so we have people now, humans in the loop, and this has not been done before. It really is surprising that it hasn't. We know the observer effect is a very important effect here, but for some reason this observer effect has never really been tested to find out exactly how critical is this observer and what does he have to observe in order to make his observation change the results of the experiment. So I'm not going to go through all of these. That would take a lot of trouble. You can see some of the conditions. I have men in oscilloscopes. Okay, they replace R1 and R2. So R1 and R2 you see are turned off. Instead, we have a line right out of detector 1 and detector 2 out to these oscilloscopes, which will put a little pulse on a screen. Okay, the men are always accurate, alert, knowledgeable, and truthful. To begin with, they're going to silently count pulses on their oscilloscope. And we can also do it with them not being silent, with them shouting it out and somebody else keeping a record of what they both say. Or they might record it with pencil and paper, or they might record it on an audio recorder. They may speak into it. Or there may be they may take a picture of that pulse, and the picture also records the time. So there's lots of ways that we can change this and make it more or less accurate, more or less objective. Okay, the screen data, which is R3, is looked at after the experiment, and we're going to then do some of these versions will be during the experiment rather than after it. We can look at it as it hits the screen. And we can have it so that neither man can see the screen, so he can't really see where the particles hit, or we could have the men actually being able to see where those particles hit. So with all of those variations, we have a set of conditions for what are the minimum requirements for defining which-way data. What constitutes an unacceptable logical conflict in PMR? Is subjective human memory sufficient as a data recorder? What constitutes an observation of which-way data? Objectively recorded versus objectively witnessed. All right, I'm going to go on to the next. And you see there's lots of discussion and further notes here. Much to read if you want to get into the details. 3 slides here just on the details of that one. So you can read that at leisure. Now we're going to experiment 4. Experiment 4 is the envelope experiment. I have a subtitle of that called a Schrodinger cat investigation. This is an experiment that I talked about. I used it as a teaching tool in many of my talks where I was doing workshops, where I'd talk about the whole of MBT, and a part of it was about science. And during that part, to explain what delayed eraser meant, I did this delayed eraser experiment, kind of a thought experiment, and I did it with envelopes. And I ran an experiment, just like you see here, where the detector 1 and 2 are on, both recorders are on, so we're going to get which-way information. So we're going to end up with a particle pattern, 2 bars, and I'm going to run this, let's say, just make up numbers, I'm going to run this, say, 20 times. And if I run this 20 times, I'm going to take this data out on R1, R2, and R3 on thumb drives or little flash drives, portable flash drives. So I'll have all the data, what's in R1, what's in R2, and what's on R3 on flash drives. And then I'm going to do the next experiment, and I'm going to take that data out on flash drives. Well, we know that all these flash drives should have the same thing on them. I'm just repeating the same experiment over and over again, taking data out on new flash drives. So I'll eventually have 20 sets of flash drives, an R1, an R2, and an R3. 3 flash drives, a little group of 3, and I'll have 20 of those groups of 3 for each of the experiment. But yet nobody has looked at any of the data. So the data is still unknown. Now, what we're going to try to do here is see whether a macro level eraser, delayed eraser, works as well as the micro level eraser, or whether there's something different about this experiment being done at the macro level and being done in this way. So after we have this 20 groups of 3, we're going to randomly take 10 of those groups of 3 and destroy the R1, R2 data. And that's destroy those flash drives. We're going to take the flash drives and we're going to burn them until there's nothing but liquid and ash. No possibility of any data ever being retrieved from them. Well, that's our erasure. We've just erased the which-way data on 10 of the 20 experiments that we have done. And then we're going to look at all the result screen data from the R3 that was collected. And what we would hope to find would be that for all the experiments where the which-way data was destroyed before anybody saw any of the results, we'll end up with a diffraction pattern. And on those experiments where the which-way data was not destroyed, we'll end up with a 2-bar pattern. So that one's up for grabs. We'll see how it comes out when we do it. Moving on to the next one. A lot more information we see here. Okay, here we have the last experiment. This is a copy of the delayed choice quantum eraser. That was done by Scully, Kim, Kulik, and Shi. Published it in 2000. This was a very interesting experiment, and I'll just walk you through it a little bit. Now, this is not the exact setup we're going to use. I'm going to modify this, and I'm going to change it in some very significant ways, but this is similar. what we will do will be similar to this. All right, so notice that we have a source that spits particles. The particle goes through a double slit. You see the two little channels there, slit 1 and slit 2 over on the left top. And they then hit a substance that creates an entangled pair. So if you look at the red lines, you'll see the one arrow goes kind of up toward D0. That's called the signal particle, or the signal of the entangled pair. And the other red line that goes down and kind of bounces off that thing called PS, okay, that's called the idler. So this is an entangled pair created from a single particle, went through slit 2, created those two red lines. So the red one with the arrow on it goes up to D0, and that's the result screen. That's where you're going to get a diffraction pattern or a 2-bar pattern, a particle pattern. That particle will hit D0 at that result screen long before it gets to the BS2, BS1, these green parallelograms that you see. Those are silvered mirrors. Well, we'll take that back. Those are beam splitters. That's what the BS stands for. Beam splitter 1, beam splitter 2. Now, a beam splitter is a device that when a photon gets to it, it can either be transmitted or it can be reflected. And it's a 50-50 chance that it'll be one or the other. So half the time, it'll be reflected up to D4, another detector. Every time D4 gets a particle in it, the experimenter will know that a particle went through slit 2, because the only way to get the D4 is go through slit 2. Okay. Now, if it transmits through that beam splitter 2, it will hit a mirror, M2, go to another beam splitter where it will either be reflected or transmitted, and end up in either D1 or D2, depending whether it's transmitted or reflected at this BS 1 and 2. So if the particle gets reflected at the first beam splitter, BS2, it will go to D4. If it gets transmitted, it will end up with an equal chance in either D1 or D2. Now, if a particle goes through slit 1, the same sort of thing happens here. So the signal particle will go up to D0, and it will hit that result screen and be recorded before that particle gets down to the beam splitter 1 and is either put into D3, which means it went through slit 1, because the only way to get a particle in D3 is to go through slit 1, or if it transmits through the beam splitter 1, it hits a mirror, M1, and then has an equal probability of ending up in D1 or D2, just the same way we had before. So you see, since there's an equal probability of ending up in D1 or D2, there's no way of knowing what slit a particle went through that got to D1 and D2. It could have come down the path 1 in the blue line and ended up in either D1 or D2, or it could go down the red line through slit 2 and end up in D1 or D2. So basically that has erased the which way data, because just because you get a particle in D1 or D2, you have no idea which slit it went through. It could be either slit, you see. So this is the delayed choice quantum eraser. So the delayed choice means that the choice of whether it gets transmitted or reflected at the beam splitters BS1 and BS2 happens after, it's delayed after the signal has already been collected and measured at the result screen. Okay, and the way they can correlate what's on the result screen with what's in the detectors, 1, 2, 3, and 4, is by the coincidence counter over on the right. So they just look at the times that these things hit these various detectors, and they can tell which one of the particles on D0 is associated with the one that was collected in the D1, D2, D3, D4. All right, so that's how the basic experiments work. Now, I won't have to go over that, but This is a slide that says how they work. How did that experiment work? And it's according to MBT's concept of virtual reality. But we're not going to worry too much with that. We have more discussion. Here is the experiment that I want to do. Now, first of all, you'll notice this coincidence counter on the right here is optional. We don't need that anymore, because if you look at R up there, it's going to look at X, the position, which means whether it's what kind of pattern it's in, and the time, and it's going to get out a probability. Now, this works the same way those other microprocessors did. Ahead of doing the experiment, we're going to run particles through both slits hundreds of thousands of times. We're going to find out where they land on D0, and we know where each particle lands. We're going to get an X and a T, and then later we'll get a probability from D0, but we'll get an X and T. So because we get T's at D1, D2, D3, and D4, those all measure the time that the particle hits there. We can just correlate those times without using a coincidence counter. We will be able to associate a particle in D0 with its partner particle that's in, D3, D4, D2, or D1. Okay, so that's the setup. Now, what we'll be able to do, if you think about the way we did the microprocessors and the other two problems, I won't go over it again, it works the same way. Here, what we're going to be able to predict is whether or not a particle will reflect or transmit when it gets to either beam splitter 1 or beam splitter 2. That is patently impossible. Because of the way this material is made, there is always a 50-50 chance, but with any photon that gets to this device, 50-50 chance whether it'll transmit or whether it will reflect. So being able to predict this is impossible, but we are going to try to do it anyway. So we will run this experiment first, collect all the data, create the probability algorithm that we will have at D0. We'll know every point at D0. If a particle hits that point, we'll be able to output a probability of whether it's in a diffraction or in a particle pattern. And we will know that prediction before the idler particle ever gets to either beam splitter. So we'll know whether we predict a reflection or transmission before that actual reflection or transmission takes place. We have 5 groups here, but 2 of them, which was experiment 1 and experiment 3, have lots of sub-experiments within those groups, trying to define exactly how which-way data is defined. What are the requirements on which-way data? So that's the 5, and what we have in these 5 is each experiment, except experiment 2, does something that's impossible. It does something that I would call it's a miracle if it works this way, because it's totally not understandable and not predictable by classical, traditional physics. I shouldn't say classical, but by traditional physics. Cannot predict it. I make these predictions based on a couple of things. One, I have to guess at what the most parsimonious process is. Parsimonious means the most efficient process for the larger conscious system to process this data. Okay, there's a couple of rules. One, time always runs forward. If you take a measurement at D0 first, then that measurement is going to change things downstream. You can't change that. There is no retrocausality. Everything happens with time running forward. Okay, and we look at each one of these interactions in terms of virtual reality and probability, and that's how I come up with these predictions. So if my predictions come true, even if any of them come true, what that will say is that this is indeed a virtual reality, because there's no other way that I would be able to predict how an atom might decay or how a beam splitter might reflect or transmit. Those are things that are impossible to do unless this is a computed reality. And this very clever experimental design puts the computer between a rock and a hard place, puts them in a corner, and they have to give up some of their tricks in order to slip out of that corner. So I have some of the things I've put in here is guesswork. There's multiple ways that you can always solve a computer problem. And the computer will always be efficient. It's an evolving computer. It's had lots and lots of time to work out the bugs and details. So I expect it to be very efficient, to take the least costly path of processing something that meets all the requirements. And the requirements are two. One, that the final result, has to not create a conflict in this virtual reality we call our physical universe. In other words, it cannot create a logical conflict there. That's one constraint that it has on it. And the second constraint is that it has to be in consonance with the rule set. It can't do anything. It can't pull any tricks that aren't a part of the rule set. So within those constraints, it needs to solve this problem that we've given it. And on the slide before this one, I actually showed how that works. All right, here's a summary of the experiments. I'll just leave that on, or you can always pause this if you want to take a little longer look at it. So this kind of wraps up all the things that I've told you in detail. We've talked about all the experiments we want to do, what their point is. The point is that they are going to lend a lot of very strong evidence that this is a virtual reality, a reality that's computed, and computed in the way that I've described in my MBT theory. That is a random draw from a probability distribution of the possibilities. Secondly, it will make it very clear. The evidence won't be quite as hard, but it will make it very clear that consciousness is the computer. Because to jump through the hoops that it has to jump through to get out of this corner that we've put it in with these clever setups, it's going to have to do things that are reactive to what we do in the design. We change the design. That's why we had a series of these designs. We changed the design. The logic of the experiment changes, and the way that the system solves the problem changes. This can only be done if the system is conscious. So we're talking about consciousness is the computer. So it produces reasonably strong evidence that that is the case as well. Well, that's it. So I hope you've had an interesting time listening to me go through these experiments so you understand them in a little more detail than what I've talked about earlier. If you think these are interesting and that you wonder how the results are going to come out, then please help us collect enough resources that we can get them done. That's what this fundraising extravaganza is all about, trying to get enough resources so that we can actually do these experiments. Because until they're done, nobody knows for sure how they're going to turn out. I'm sure there'll be lots of opinions, but opinions are just opinions until the experiment is done. After that, we have facts. So I'm interested to know what those facts are, and in either case, however they turn out, whether they turn out the way I predict or not, I will learn. It will help me understand better the way the consciousness system would choose to solve the problem. There's, like I say, there's always multiple solutions. I've picked the one I think it will pick, but I can learn a lot from these experiments no matter how they turn out. They will be very helpful. That's why we do experiments. We learn whether our predictions are true or not. We learn a great deal from them. So please help us get these done. Thank you.